My pleasure. Huh?
Yeah, thank you so much. Yeah, thank you.
Yeah.
He was secretary for nearly 6 years of Humboldt Academy Pune, and he raised the bar so much high. Now I struggle to maintain that.
You have increased furthermore, Gopi.
And then
it's all. I think it's all blessings from very dynamic senior people like Professor Rao, Professor Ramaswamy, Dr. Arnab Kulkarni. They gave us guidance. Yeah. So it all went because of their guidance. That's more important for us. Yeah.
I was in Karlsruhe in 84, 86.
Yeah. Apparently, great.
I was in Karlsruhe in 84, 86, and at that time it was called Kernforschung Syndrome.
Yeah, exactly. So they made the huge structural change.
Yes.
I
used to stay in the guest house of at that time Hirschstraße in Karlsruhe.
Is it on Campus South or is it in the city?
Yeah, in the city. They had a guest house.
Okay. They now call it Campus South and Campus North. So the Forschungszentrum is now the Campus North because it's in the woods, and we are here close to the. So I'm in the physics building. So this is the very tall building that was probably already there in 80. I think it's from the 1960s. So it's insanely ugly, but it's nice if you can look out of it.
Yeah, that was my first visit. So.
Sorry?
84.
Yeah.
90. You were born at that time? I don't know.
I was not born at the time.
That's a good one.
That's quite good. That's how long the Humboldt Foundation is already around. Huh? So
yes.
To all the speakers, actually, I want to introduce Professor Madhav Rao, who is the president of the Humboldt Academy. And he has a lot of experience. He was a former professor at Pune University. Of course, now he is retired actually. But and then we have Dr. Ramaswamy. Maybe Dr. Ramaswamy is up. Yeah, so he is also one of the senior most member. He was also in Karlsruhe, if I am correct. Is that right?
Wow. Okay.
I was in Erlangen.
Oh, sorry, Erlangen. So he was in Erlangen.
And, also beautiful. Yeah.
Yeah. Arnab Kulkarni, so he's a Humboldt fellow, but with agricultural background. So he has done some very fantastic work. If you happen to talk to him, his experience will be really, really different.
I was in Göttingen. Göttingen.
That's
1965.
Cool. That's where I did my PhD. Huh?
Yes.
Spent there almost 8 years of my life.
Really? Oh, great.
Excellent choice.
Exactly. Yeah.
What field did you do back then? What field are you?
In 67, I was there.
67.
67. Economics.
Okay. Yeah. Great. Yeah.
Philip, he can correlate how the onion price and the election results can go together in India.
Is there a correlation or is it just a joke?
Is
there really
there.
Okay. Does it go up or down?
It depends.
No, they will go up now.
When is the next election in India? I actually don't know. So,
it's another 4 years.
Oh, okay. So
at least 3.5 years. Yeah.
So low price onion. It's good.
Okay, good.
And Srivatsan, he's our treasurer. So who controls all the money?
No, that is somebody has to do that. Huh?
So good. Sartale, can you switch on your video?
Yeah, I wasn't born.
In Bonn. Oh, that's also very beautiful. It's very close to the headquarters, huh?
Yeah. So I was living in Bad Godesberg.
Oh wow!
So it's just it's along the same street as the Humboldt Foundation, actually.
Wow! You must be a rich man. They were
no.
Yeah, that's why.
Treasurer.
That's why you have made him a treasurer.
Yeah, right. You never put poor people as treasury, right? This is very dangerous.
And then last year I was in Constance for a renewed research stay.
Ah, oh yeah, that's beautiful. Lake Constance is very nice. Yeah.
That was a nice, good experience actually.
Yeah, I can believe so. The south is usually more. I'm from the north. The north of Germany is usually ugly. And the south is more beautiful. And the Constance is the very south, and you're almost
it's very south. Yeah, it's just border Switzerland, Austria, so it's nice.
Yeah,
it was a nice stay actually, both in terms of culture as well as research.
Yeah. So you came back after a long time to Germany, or have you been in the?
No, I usually visit once in a while.
Yeah,
and 3 years back I was there again in Germany for 3 months. And then in between, I have a good connection with Germany and faculties, because, all my peers, like, people who are doing PhD as well as postdoc in Professor Famulok's lab in Germany. So almost all are in academics. So I have a good, same age group or similar age group. I would say I have at least, a reasonable number of peers who are actually in academics. So that helps a lot, and we are in similar field also. So it's nice.
Great.
Yeah.
What field are you working in?
I am working in chemical biology and especially nucleic acids.
Okay, cool. That's way too complicated for me. I like simple atoms.
Yeah.
We're going to talk about that.
Okay, great.
So,
yeah, I'm just waiting.
Sorry.
Yeah.
Sorry to interrupt you all. So we are now started live streaming in YouTube. So it is online.
Okay.
And I just request all of you, if you have opened simultaneously YouTube and all those things, that sound is coming up.
No, we have not opened.
No, we are not.
Okay.
My pleasure.
Thank you so much.
I'm just waiting for the first speaker to join, actually. Louis, when she joins, actually, we'll start quickly. Because now we are very close to 4:30. I sent a mail also, so I'm sure she will be joining.
So, Buddy, you're the host, right?
Yeah.
So you're the host in the sense you can mute, unmute people, or how is it?
No, that Ramrup will take care.
Okay, Ramrup will take care. Ramrup, once we start, you can mute except the speaker, and then if they have questions, they would raise their hand, and then you can unmute them, or they can unmute by themselves. That's okay.
Yeah. But then I will tell all those things in my,
No, I'm just saying.
I will do that.
I'm going to tell actually.
Okay. Because we always do this online class. We have been doing it for the last few months now.
Okay.
Yeah.
For lockdown, so we know what sometimes certain problems can come, and then we sort it out.
So are you all in lockdown right now, or is how's this?
No.
Partial lockdown. I mean, not. It's about 40% open. I guess I should say.
Welcome, Louis. So first speaker has joined actually. Good afternoon, Louis.
Good afternoon.
Yeah. So we were simply chatting for some time till others join. So maybe, buddy, can we start? Now we have all the speakers.
Yeah, you can start.
Everybody's there? Yeah.
Yeah.
Should I start or we'll wait for some time?
Hi, buddy.
No.
Hi.
Start.
Hello, Rajiv. How are you?
I'm fine. Good to see. This is wonderful meeting here. I'm waiting for this.
Yes. Really true.
Please start.
Hi, Rao.
Hello.
Rajiv is wearing a 3D glass or what?
Huh?
No, it is reflective.
Rajiv is using a 3D glass.
So I think we should start.
Yeah.
Okay, but you start, yeah.
Yeah. Very good afternoon to all of you. Professor Madhav Rao, President of the Humboldt Academy Pune, distinguished speakers from Germany, Dr. Judith, Dr. D.N. Fisher from Humboldt Foundation, fellow Humboldtians from Pune and Mumbai, student participants, friends, ladies and gentlemen. On behalf of the Humboldt Academy Pune, it gives me great pleasure to welcome you all for this 4th mini-symposium organized by the Humboldt Academy Pune. Our Humboldt Academy Pune, formerly called as the Humboldt Club Pune, was founded in 1972 by late Professor Abhay Kulkarni, a German language professor from Pune University. There are more than 100 Humboldt clubs all over the world, and established by alumni, Humboldt alumni, and 10 of them are in India. In fact, the Humboldt Club Pune is the oldest club amongst these 100 clubs. From 1972 onwards, this Humboldt Club Pune worked on many years on ad hoc basis, with occasional meetings without any written constitution. There were hardly 8 to 10 Humboldt alumni during those days, And later on, number of Humboldt alumni started increasing in Pune, and in 2004, the club was formally established at NCL Guest House, thanks to NCL authorities for giving these facilities to Humboldt Academy Pune. And constitution was drafted, office bearers, executive committee was formed, and in 2017, somehow we felt that Humboldt Club is not a good name, So we thought we should change it. And then in 2007, the Humboldt Club Pune was rechristened as Humboldt Academy Pune, and the website was created. So currently we have about 45 Humboldtians in Pune, and it is the most vibrant Humboldt Academy in India and the entire world. Okay. We had several senior Humboldtians like Professor Karve, Professor Ramaswamy, Professor Saurabh Pal as the past presidents, and currently Professor Rao is the president of our Humboldt Academy Pune. Yeah. The objectives of our Humboldt Academy Pune is to promote scientific and cultural interactions, between Humboldt alumni within the country by organizing seminars and colleagues. We organized, as Gopi mentioned just now, we organized 4 big colleagues, very successful colleagues, fully supported by Humboldt Foundation. And 2 were in Alibag area, the coastal of Maharashtra, and 2 were in Goa. We had more than 100 participants of Humboldtians from Pune and Mumbai, 14 German professors, and representatives from Humboldt Foundation, and then 30 to 40 students in each college. In fact, the students' participation, a flash presentation, and posters were excellent. I tell you, it was liked by everyone in the Humboldt College. And of course, the topics of the colleagues were very versatile, with themes like science, globalization, and human development, a sustainable development, mega trends in 21st century. We also organized a joint DAD. We have close interaction with the DAD of local chapter of DAD of Pune, and we organized the workshop on DAD Humboldt on the topic, the science and art of sustainability. Besides these colleagues, we also organize mini-symposiums. Of course, the 4th one is the present one. We organize meetings with PhD students from local institutes like NCL, ICER, Pune University, and we identify potential candidates for Humboldt fellowships. We encourage them to contact German professors and write good proposals and apply for Humboldt fellowships. We have regular meetings with all our Humboldtians along with their families, and we felicitate our fellow Humboldtians for their award and recognition and contribution to the science. We have wonderful meetings regularly held by our Humboldt Academy Pune. You can see that our Humboldt Academy Pune is very vibrant. Now I once again welcome all of you for this 4th symposium and hand over the mic to Dr. Gopinath, and who will give the details of this symposium. Thank you very much.
Thank you very much.
Thank you, Dr. Badigar. Good afternoon to speakers and participants from Germany, and good evening to participants from India. Indeed, it is a wonderful experience organizing this fourth mini-symposium of Humboldt Academy Pune. Every year, Humboldt Academy Pune is organizing a mini-symposium with distinguished speakers. And as he mentioned, actually, all the mini-symposiums are very good success. In fact, the last symposium we fully recorded, and it is still available on our website. So when you have time, you can have a look at it, actually. In that series, we decided to organize the next mini-symposium about 6 weeks ago. Initially, we were worried about the ongoing pandemic, and that too, Pune is really the hotspot of COVID-19 pandemic in India. But however, we decided not to budge to the pandemic, but rather conduct the symposium online, as it is the norm of all the meetings in India and elsewhere. So we also wanted to catalyze the Humboldt Academy activities by conducting this mini symposium. Otherwise, it was dormant for about 6-7 months actually. So next came the discussion on scientific program of this symposium and whom to invite. So initially we decided we will approach those speakers who could not make it to the Humboldt Colleague, what we conducted in January 19. So indeed, we approached Professor Christine Pape, who is the president of Humboldt Foundation, and Professor Thorsten Posselt, who is the director of the Fraunhofer Institute in Leipzig. However, due to their busy schedule, they could not accept our invitation, but they conveyed their best wishes actually. However, our first speaker, Dr. Louis Fischer from same Fraunhofer Institute, Leipzig, readily accepted our invitation. So thank you very much, Dr. Louis, for accepting our invitation. And while we were planning to approach other speakers, then Professor Madhavrao suggested that we should conduct something like Humboldt Science Slam, because he was the only one who was invited from our Humboldt Academy to attend the Humboldt Congress, which was held in June 2020 actually. So he said, why don't we conduct something like that? Then we had a discussion. So he said he was very much impressed with the presentations made in Science Slam. So in fact, all three speakers are there actually. So he has seen all of you, and he heard all of you also actually. So that is something I want to tell you upfront actually. So we decided to approach all the 4 speakers of the Science Slam. And in fact, see here, those who know about the Humboldt Foundation, they also know about the high quality of the program they conduct. So, and I had no second thought on the high quality of the speakers. So I'm really, really pleased about that. In fact, Ms. Dan Fisher from Humboldt Foundation and Ms. Judith Schilt, actually, both of them helped us in giving your communication details. So after that, I wrote email to all of you. All the 3 of you accepted actually, and of course, one of the speaker could not accept because she was busy in something else. Anyway, I thank both the Humboldt Foundation for giving us the communication details of 3 speakers, and all the 3 speakers also I want to thank past actually. So when I looked at your webpage, actually, both I mean all the speakers actually, I was really amazed at the quality of the work they have done as well as reported in the literature. I'm sure this evening we are going to witness a treat to our ears and as well as eyes with the presentation. So I request all my fellows Humboldtians and others participants actually sit back, relax, and enjoy the lectures. Normally in webinars, actually, the question and answer sessions are really, really small, few minutes we give actually, but then we decided we'll be a bit liberal actually, so that, more question and answer session, can be done online actually. So I request all the participants to type your questions or comments in the chat box, which is available online actually. So you don't have to wait till the end of the seminar. So even during the seminar, you can start typing your questions actually, so that the questions are available. And our session chairman, Dr. Badigar, will entertain as many questions as possible. If time permits, we can have direct interaction with the speakers. That is also possible. Again, it depends on the time. So except the panelists, that is all the 4 speakers, myself and Dr. Badigar, who is the session chairman, and Ramru. So all others, mic and video will be switched off during the presentation. So because this is mainly to conduct the whole session uninterrupted. Except for the first talk, we are also recording the symposium and we will upload on our website. So Louis is also aware of that actually. So with that, actually, Humboldt Academy Pune functions like a family. So there is a team behind who are responsible for this event, and I thank all of them. In fact, my colleague Dr. Srivatsan will finally make a formal vote of thanks at the end of the symposium. So I will not go too much into the detail. With this, I conclude my short speech and on the organization of the symposium. And now I don't want to stand between speakers and the audience. So I now request Dr. Badigar to take over this and conduct the entire session. Thank you very much.
Thank you, Dr. Gopinath. Yeah. Let me introduce the first speaker. As Gopinath already mentioned, kindly mute all your, and then only the speaker can, talk. So, Dr. Louis Fisher. Yeah. So it's my great pleasure to introduce Dr. Louise Fisher. Dr. Louise Fisher obtained her PhD from University of Edinburgh, Scotland, UK, in the area of human geography. Then she moved to Fraunhofer Center for International Management and Knowledge Economy in Leipzig, Germany. In 2015, and working as a researcher and project manager in Fraunhofer Center for International Management and Knowledge Economy. She has expertise in the analysis of science education system, in understanding the transformation processes and innovation policies concerned to Northern Africa and Western Asia. One of her key projects focused on understanding the potential of frugal innovation for various contexts. Since 2018, Louise is also a fellow of the Arab-German Young Academy of the Sciences and Humanities. So I request Professor Louise Fisher to give her first talk on frugal innovation. I request Louise Fisher.
Thank you very much. Thank you very much. Can you hear me properly, first of all? Okay, wonderful. So thank you very much for the invitation. It's my
frugal innovations like business models, critical success factors, global challenges, how frugal innovations can help to address these issues. The talk is open for questions. Yeah. Any questions?
Questions are listed in chat box.
Oh.
Yeah, I'm checking the chat box right now. But you want to moderate it? Do you want to answer each question?
Okay, I opened it.
Okay.
So let's see. I think Gopinath has asked.
Maybe I'll ask my question, Louis.
Yeah.
That's the last question. Our politicians are highly short-sighted, and they don't invest in something that will not give return quickly. It is something like the last question what you posed. That is the climate change. Finding a vaccine for COVID-19. Though we know that that kind of pandemic is going to happen again and again, but still they did not invest in finding a vaccine for such a thing. So I mean, basically, they don't want to invest, which will not give return quickly. So how we are going to educate these politicians? So this frugal innovation is really important, actually. But then, such a big problems like climate change, vaccine, all those things are going to be even more important. So I don't know how we are going to educate these people.
Okay, this is a very complex and difficult question. I have a partial answer and I have a question. I didn't know that Indian politicians, because frugal innovation is big in India. It's not been researched maybe, but it is really, India is one of the markets or countries is really successful in producing products and services that are good and of good quality, but with a lot less cost. So I'm surprised that the politicians are not aware of that. But as a keynote, as an adult, how do you convince someone? I would always say with success. If you have a company like the Mars mission, it's a typical example. You have a successful story, and if they see success, then they usually buy into it. So you have to produce results in some way. I don't think that educating, if someone doesn't want to be educated, like mind changes is so hard. We figured in this project, this is the biggest challenge actually. You can change the way you do your management. You can change your partners. This is difficult as well though, because it's both interrelational relationship question sometimes, you know, changing your network is always not that easy either, but changing the mindset of somebody who doesn't want to be changed, this is a big thing. So I would say success, but that's just my intuition. I don't have the answer for this, but I do know when, you know, someone tells you, I just do it, and then you come around and you come up with a really, really good solution that's working, then people will listen to you. But yeah, so Indian politicians are not aware of frugal innovation then? Is that
no.
what I'm
I mean, this is a general question at international level.
Yeah, okay, understand.
When when a person occupies a powerful office like a US president,
oh yeah.
And if he don't believe science, you know, it's really going to be a problem to the whole world, actually, not only the US.
That is actually, to me, one of the big, climate change is a big challenge, and there are many big challenges, but I do see almost a crisis coming in the role of science in society. So all we can do is advocate and be strong and do good work and lobby for ourselves, maybe. But what is happening in the US and triggering to some other countries is definitely dangerous.
Okay, I think let's go to the next talk question by Professor Madhav Rao.
Yes. So actually, there's one important question which I also have. Is from Nandini Devi, NCL, and she has a very, very interesting question. What she says is frugal innovation, is frugal misunderstood as lower quality? Is it misunderstood as lower quality?
Very good point. Very, very good question. We had that question too. I didn't touch on it here. Yes, in some contexts it is. So we've been recommending some companies in Germany to not speak of frugal, but to call it smart innovation or something else, but to take the values. Because yes, for some people, the word is, they associate something of low quality with it, even though there's no reason for it. But yes, if as we used in academia, because we know it's the word that's been used first to describe it, you're absolutely right. If people associate something you don't want it to be associated with, you need as a company to change your branding and the words you're using. Absolutely. Very good question.
Thank you. So that's not my one, Nandini Devi. Yeah, thank you very much.
Yeah, let's go to the question from Dr. Avinash Kumar. How do you sustain frugal innovation? Dr. Avinash Kumar?
He asked, no, he won't come. You ask her, that's all. There's one more question from one colleague who says, how do you sustain frugal innovation? How does it sustain itself?
Okay, I do not understand it. What do you mean by sustain? Because they're not disruptive and they're not innovative and then they will not lead the market? Or what do you mean sustain?
Yeah. Sustain, how does it work? How does it make profit? Because basically a company needs to make profit, right? So how does it sustain by itself?
Economically, you speak.
Yes.
Yeah.
Okay, I will tell you what I think I've understood and what we found. So in general, if you like in Germany, let's say, I'm just taking the example of mobility because we looked at it, right? So we had a lot of conversations with people in the car industry. And they were like, okay, what you're asking for will not be a car anymore according to German standards. And I'm like, okay, well, but we do know that, as I've said, the younger generation and the older generation do not all have to have high complex cars, because to them the idea of status, and there was a big thing in Germany, and for some it still is, your car represents your status in society. So if you want to be someone, you should have a good expensive car. So you demonstrate this to the rest of your neighborhood here. But this is changing, especially in the younger generations. They do not care about status anymore, or much, much less. So with that, you have a new customer, you have new customer values. And if you understand these customers, you can develop a car like the Dacia, or call it a vehicle if you don't want to call it a car, but something that these people want, because the younger generation in Germany is environmentally friendly. They go on the streets, in order to do something against climate change. So they will be receptive for any kind of solution. And in the end, we found that what is happening now is they didn't really change the cars, but what is super successful is car sharing. So successful now here. So people do not own the car anymore. You just, if I want to go shopping, I have an app and I can rent the car for, I don't know, X many hours. I don't have to have it. I don't have to own it. So I'm sharing the car with thousands of other people. So what I'm trying to say, if you find your customer niche and if you understand your customers, you can develop a product or a service like car sharing in this case, that will be economically sustainable. But yes, if you don't have it,
Thank you.
if you're not customer oriented.
Can we go to a question from Rajiv Kumar? Rajiv Kumar is there?
You ask.
He asked a question, affordability. Yeah. He asked affordability is time and region dependent. Can you address this?
Basically, my point was, buddy, whatever is affordable in some part of the world is not affordable in another part of the world. So how the innovation can be global and competitive? The frugal innovation. Just a simple point.
Good question. Very good question. This is relative, of course. And as I said, frugal means customer orientation. It is unlikely that you produce a product for the entire world. You need to know whom you're working for. Are you solving a problem for Delhi? Are you solving a problem for a particular neighborhood in Delhi? Or are you solving a problem for, I don't know, Fort Lauderdale in Florida? This is people have different needs and desires, and it depends. There is no affordable, maybe it is, but no, it isn't. No, we do know it is not. You're absolutely right.
Okay. Yeah, so that means that the frugal innovation per se is basically for local people, local market or local society, and it will be difficult to globalize it.
It doesn't have to be for local. You need to find people who are asking for the same thing. Okay. And then if you're a company, you can do price discrimination. These things, you might sell the same product in Germany and sell it a little bit higher, and you might sell it in, I don't know, another country, and then you sell it to a lesser price, but in some it still covers your costs and your branding improves. There are different business models.
Okay, so it's more of a marketing and business strategy. Okay.
Not only, but also. Okay.
Also, yeah. Also. Yeah. Okay, thank you. Okay.
Yeah.
Thank you. We can go to the next question by Dr. Arun Kulkarni. Do you like to ask the question? Hello.
I'll ask actually. Innovation in packaging could probably some scope for frugal innovation, like sachet for packaging shampoo. It's very popular in India. So that's a kind of more of a comment actually. Maybe I have one last question actually. Is supply chain management actually now actually all the countries are thinking to change in a different way, because predominantly it was dependent on China. Now it's going to change after this. Even now actually all the countries are thinking how to change that actually. So in what way it is likely to change?
Okay, I have to ask you again. Thank you, but in what way supply chain management is going to change?
Yeah, I mean it's kind of it should be more of distributed supply chain management. That's the concept slowly coming up actually, but I don't know how it will change. After the pandemic.
I have to be. I'm very afraid, but I don't feel comfortable. I don't think I can answer your question. This is too big. Maybe we can discuss this as a group, but I don't think I have the answer.
Okay.
Because this is something, yeah.
Okay. So I think because of lack of time, I think we'll stop the discussion at this time. Thank you so much, Dr. Louise Fisher, for a wonderful talk. I request all of you to join hands for appreciating her talk. Thank you. Yeah. We'll go to the next speaker. Hello. Yeah. We'll go to the next speaker, Dr. Arnab Muhuri. Hello.
Hey, go ahead.
Hello.
Buddy, you go ahead.
Yeah, okay. Yeah. So Dr. Arnab obtained his PhD from IIT Bombay in 2018. And he's currently an AVH Alexander Van Humboldt Fellow at the Heidelberg University. He was also a visiting fellow at the University of Tokyo and Niigata University, Japan. There he did research on machine learning techniques for satellite imaging applications. He is currently involved in the development of under canopy snow cover mapping algorithms with satellite SAR and optical images over the Black Forest, Germany. And is also visiting scientist to CSDIO, Center for the Study of Biosphere from Space, and CNES, the French space agency in Toulouse, France, for large-scale implementation of his ongoing development for the Earth observation algorithms. Dr. Muhuri, he will take us from Himalayas, from India to Nepal to the Black Forest, Germany. I request Dr. Arnab to lead his talk on the satellite Earth observation.
Does such diversity exist? We are a vibrant and noisy democracy. And if you ask me, we should oppose it.
Please, and yeah.
Yeah, am I audible to everybody?
Yes.
All right, thank you. So let me begin by thanking the Humboldt Academy Pune for this wonderful opportunity. And I would like to thank my colleagues at Humboldt Foundation in Bonn for connecting me to you all. It's a pleasure to be here today. Now, I'm connecting from Toulouse, from south of France, and Toulouse is a well-known city for French space agency and for its aerospace industry and aerospace giants like Airbus. Today, I want to talk to you about my journey from India to Toulouse via Germany. So let us go back in time. In our geography lessons in school, we learned about something called spheres. We were told that everything on the Earth can be placed into 4 major spheres, but you can categorize them further. A section of the hydrosphere deals with the frozen section of the Earth, and this is known as the cryosphere. Now, there are different elements of cryosphere, like glaciers, permafrost, polar ice caps, and snow-covered areas. We can imagine these frozen elements as our assets, like fixed deposits and mutual funds, which is going to repay us in the long run. When we look at the spread of the snow-covered areas in both the northern and the southern hemisphere, we realize that its extent is quite prominent as compared to the other elements of the cryosphere. Look at this reflectance curve and tell me, what do you find particularly distinct about fresh snow? It's the reflectance, right? So among all the elements of the cryosphere, freshly precipitated snow has got the highest reflectance. It can typically reflect over 90% of the sunlight depending upon the grain size and the contamination level of the snow crystals. Now, that's not only that, but of all the natural material present on the Earth's surface, fresh snow has got the highest reflectance as well. Now, you may ask, how does that affect our life? Small changes in the reflectance, such as lowering of the reflectance due to snow contamination, due to pollutants, or changes in its areal extent, such as reduction, can cause exposure of water surface, and that can significantly affect the global energy balance. It is therefore necessary to better understand the seasonal variation in the snow cover extent over our planet in order to understand its impact on the climate. And that's why there is a sense of urgency in the scientific community to observe the cryosphere in very close intervals. The next question you would like to know is, how do we observe these snow-covered regions? Imagine you would like to have such a map at a weekly interval. How do you do it? Well, there is just one practical solution: satellite observation. Now, apart from getting alarmed by the depreciating state of the cryosphere, what can you do with this information? let's take an example. Here, we are looking at the snow-covered mountains in the Himalayas, and you can notice how the snow correlates with the high elevation areas. So how do we use this information? If you can identify the aerial extent of snow cover over the mountain, you can estimate how much water is going to be released out of the mountain during the forthcoming summer. This information can be utilized for forecasting the power potential of the hydroelectric power plants connected to the streams that are coming out of this mountain range. So even before the snow melts in the summer, you're able to predict the amount of electricity you will be able to generate and then estimate the load on the other energy alternatives like fossil fuel and renewable resources. And this is one way you can forecast the import demands for commodities like coal or oil. So you see how snow over the mountain can actually be connected with the national economy. Forecasting from photographs over snow-covered region is not a recent practice. Around the 1940s, the snow hydrologists started using ground-based photographs to predict snow melt runoff. And the years later, people started flying with cameras over test site for a wider aerial view. A popular civilian satellite mission called Landsat-1 was launched by NASA and the United States Geological Survey in the year 1972. Landsat is the longest running Earth observation mission in the world, with Landsat 8 presently in orbit and Landsat 9 already planned. These satellites carry multispectral optical sensors, which are extremely reliable for monitoring snow-covered areas due to the distinct reflectance of the snow measured by these satellites. The basic principle behind any satellite sensor is that there has to be a source of energy or illumination. In case of optical satellites, sun is the source of energy. And what the satellite measures is the reflectance of different material present over the Earth's surface. The reflectance of each wavelength is stored as a number in a matrix. You can imagine a multispectral image to be a cube of stacked matrices with each matrix representing a wavelength. So if you consider one pixel and you cut through the cube and you pull it out like a piece of cake, you will have the spectra of the material that was covering the pixel. But if you have a day like this, when the sky is obscured with thick layer of clouds, you cannot do much with the optical sensors. Your pixels can either partially get corrupted or the cloud signatures can completely obscure it. So these are the three primary limitations of optical satellites. They only work in presence of sunlight, since they are passive sensors, so they can only collect the reflected spectral information. They are of no use if you have clouds, thick clouds, and the detection of snow cover under the forested landscape is a challenge. Now, during my doctoral thesis over the Hindu Kush Himalayas, I addressed the issue of observing snow-covered areas in absence of sunlight and under cloud-obscured condition with satellite radar sensors. The Hindu Kush Himalayas feeds the major Asian rivers in the Ganges, and it is the largest collection of snowfields and glaciers outside the polar region, and hence it is also called the third pole of the world. The meltwater from a seasonal snow cover flows into these rivers, and it feeds almost a seventh of the world's population. So this area is one of the most populated, the most polluted, and the most water-stressed region of the world. Now, over the past few decades, there has been some uncertainty regarding the state of the cryosphere in this region, which is evident from these publications. Due to the high altitude of the Himalayas, most of the snow-covered area lies above the main tree line. And this is a good thing when you're observing with satellites, since it avoids image pixels with mixed information. Due to the unobscured nature of the area, satellite radar sensors were an ideal choice over this region. Unlike the optical satellite sensor, the radar sensor generates their own source of illumination, so the observations are nearly independent of sunlight or cloud cover. The primary difference between an optical and a radar sensor is the way they look at the target. Radar signals are typically characterized by imaging wavelength and the sensor polarization. So a typical radar imaging geometry looks like this. It begins with targeting a polarized antenna that generates a propagating electric field in space. The polarization of the wave is determined by the orientation of the oscillation of the electric field with respect to the Earth's surface. Now, the signal directed towards the Earth can get scattered in several different ways, and we record those scattering back in the sensor. And this is how we construct the scattering matrix with this received information, which defines the average scattering characteristics of different targets located within an image pixel. The target is characterized by a scattering matrix, so you can imagine it as the spectral information of the target in the radar wavelength. When the electromagnetic wavefront approaches the target, these are the possible scattering scenarios. And what we are essentially looking with radar sensors is the behavior of the radar signal at dielectric boundaries. The first boundary before the penetration of the incoming radar wave is the air-snow boundary. And within the snowpack volume, we have several intermediate boundaries because of regular melting, refreezing, and ongoing precipitation events. The dielectric state of the snowpack actually determines the penetration of the wave, and hence the interaction of the incoming electromagnetic signal with the snowpack volume. Therefore, the snowpack volume is wet or it is dense. It creates a sharp dielectric contrast, which means the wave then gets reflected back. Now, radar backscattering varies quite substantially with the dielectric state of the snowpack volume. The water molecules are separated by these hydrogen bonds, and at temperature below these molecules, below 0 degree, these molecules assume the most stable configuration by reorganizing neatly and strengthening their hydrogen bonds, which otherwise is quite momentary in liquid state. This is the reason why we see crystalline structure of snowflakes under frozen condition. Now imagine a parallel plate capacitor, another way to understand this, and you fill this up with dry snow, and you apply electric potential across the plates. Now in this case, the migration of the hydrogen bonds are restricted in dry snow because the molecules cannot move. So the molecules cannot be polarized. In the dielectric term, dry snow is a weak dielectric material, since a strong dielectric material will be the one with high polarizability, which means one should be able to polarize or align the charge centers in accordance with the polarity of the applied electric field. And this is only possible when some liquid within the dry snow volume is present. So now you can probably imagine why the radar signal finds it hard to penetrate through a wet layer of snow. Now, snow crystals are anisotropic in nature, which means that the incoming wave gets scattered in different ways in different directions. So it's not an isotropic media. These are some publications which came out of the investigation over the Himalayas. Now, let us move forward and let us go to the Black Forest. Yeah. Now, satellite mapping of snow cover in forested environment is a different challenge altogether. And this is so because you have a layer between the sensor and the snow cover, which is lying on the forest floor. And this is how a segment of the Black Forest looks from 750 kilometers above the Earth's surface. In forested landscapes, the overlying canopy volume creates a barrier between the layer of snow and the satellite sensor. This is a watershed, which means all the snow that melts in the valley contributes to a river, and this river flows into the River Rhine. River Rhine plays a very crucial role in Germany in terms of both economy and culture. It flows through important cities, supports agriculture and tourism. So my ongoing investigation over the Black Forest deals with development of algorithms that can look at the snow dynamics under the forest cover with satellites. If you consider the average altitude of Black Forest, that is quite different from the Himalayas. Unlike the Himalayas, we are always below the mean tree line in the Black Forest. So open areas in this region are quite limited. Almost 80% of the area is covered with forest. So during the winter, the snow is outside the forest, which can be detected without any ambiguity, but there is also snow under the canopy inside the forest, which is the problem I'm trying to address. So how are we addressing this problem? The most important aspect of the investigation is to understand the forest structure. We can get an idea about the canopy structure using special kind of lenses called fisheye lens. These lenses are known for their ultra wide angle view. So it essentially recreates the same view as if you were standing under the forest and looking upward towards the sky. And what you see basically is how much of the forest canopy is overlying that particular point. And this is important, since one of the main reasons why we are unable to observe snow over the forest floor with satellites is because forest absorbs a lot of visible component of the light. And this is the component we are dependent on when we are observing the snow cover, because snow exactly reflects strongly in this component. Now, we also have a network of observatories around Black Forest that measures meteorological variables. The effect of climatic forcing is important because we need to explain the dynamically changing extent of the snow cover between the satellite acquisitions. What is also unique about this investigation is the use of cameras inside the forest to observe the snow dynamics, and we correlate this information with the satellite measurements. And these are some articles which came out from this investigation over the Black Forest. Now, we have one more challenge left. Look at this scene. It's a complete satellite scene, and it covers quite a vast area. And we realized that what we were observing before was a small portion of a much larger satellite scene. Such scenes are several gigabytes large and not even covering the entire region in the single scene. And when we move further, such scenes only a small portion over Europe. So you have hundreds of such scenes if you're looking over a small portion. And if we zoom out at the country scale, we have thousands of such scenes just in one season. And this is what brings me to Toulouse. I am here to scale things up. Such kind of applications are processing intensive, and therefore I'll be employing these algorithms on a high performance computing cluster of the French Space Agency. In the forthcoming months, my objective will be to upgrade the state of the snow cover algorithms utilized by the European Environmental Agency for improving the operational services. And so this was a bit about my journey from India to Toulouse via Germany. Thank you so much and have a nice day.
Thank you. Thank you very much. Hello?
Yes.
Hello? Hello?
Hello?
Arnab, there is a question for you. How the radar works to understand the polar ice sheet? You can see in the last question in the chat box.
Okay. Okay, so the question is how the radar works to understand the polar ice sheets. So I'll give you an example. What's typically happening with the polar ice sheet. So especially during the summers, what happens is that there are formations of small water pools, and these water pools are good absorbers of heat. And once the water starts heating up, it starts heating up the ice around it, and you are stuck in a circle. So the water heats up, it melts more ice, and then it collects more heat, and then melts more ice. What you can do is you can actually monitor these pools with radar sensors, and radar sensors are excellent choice because you don't have to depend on the energy source. It carries its own energy source. You can image the area 24/7. So and even during cloud obscured conditions. And like I mentioned, radar sensors are very sensitive to the dielectric. So if you have water and if you have ice in the neighborhood, you can actually detect. And what radar sensors does is it has got an extra capability to penetrate. So you can even see coming which are not maybe on the surface with optical sensors.
Hello? Hello?
Disconnect audio.
Yeah. Is it audible?
Yes, am I audible?
There is some problem. There's some problem. There's some noise coming. Please unmute. Yeah, please unmute those who are. Yeah. Okay. Dr. Arnab was the one. Dr. Arnab was the wonderful talk. Hello.
Yes. Watson, you can ask your question.
There is someone he has to mute, I think.
I'm muting.
Hello.
There's a person W. They have to mute actually. Huh?
I done. Don't worry, I'm muting.
Okay, so Arnab, can you listen to me? I'm Sri Watson.
Hello.
Yeah, Watson, go ahead. Yeah, Arnab, there is a question for you.
But then I'm not sure if he is able to listen to me.
No, Arnab is there actually.
Hello, Arnab.
No, there is some Gopi. There is some problem with noise. Everywhere the noise is coming.
No, now it's fine. Now it's fine. Then, I'm not sure if Arnab can hear me now.
Arnab, can you hear?
Hello.
Arnab.
Arnab is unmuted, so
yeah.
No, but then he's not answering. That's why. His video is also lost. Probably he'll come back.
I think some network issue maybe.
Yeah, so he'll go back and.
No, maybe so you can type your question. I mean, those who have question may please type your questions in the chat box.
Gopi, can you hear me? Because I am having a problem with hearing.
Yeah,
I can hear.
We can hear you.
Okay. I think there is some.
Your voice is also a little low. Probably you have to increase.
Arnab is back.
Arnab is back.
Arnab, can I question? Yeah, you're able to hear?
Yes.
Okay, Arnab. Great talk, man. And then it was quite informative. And then it's a little different than what we usually hear. See, the question is that, the thing is that, so you have a satellite system. Yes. And then for any satellite system, you have a cross section, right? The reflection cross section, which you can measure, right? And it would be distance dependent and other things and all. So now let's say for a vast area, for Black Forest, it's okay. Like, you have 110 kilometers by 110. But then In order to map Himalayas, do you think you can work with one satellite, or you need a multiple source of data and to have a, I would say, more comprehensive picture? You correct me if I'm wrong.
Yes. So this is not the only SWOT we have.
Hello.
Arnab, your voice is very, very low. Can you come closer to mic?
Is it fine now?
Yeah.
Okay. So to answer your question, this is the SWOT from Sentinel to mission from the European Space Agency, and there are other missions which has wider SWOT. Like for example, you have MODIS, which has got a huge SWOT with. So you can go for such missions. So what we essentially do when we are mapping over a region is that your satellite pass only happens over a single orbit, over a single path. So basically, it's not that every day you can get the entire Himalayas covered. So you will have to, of course, combine, like you said rightly, and that's what we are also doing at the French Space Agency, and that we are combining satellites from USGS and NASA and the European Space Agency and other sensors, and because all of them crosses at different time intervals, and maybe we can get a good enough picture for a week's time. Yeah.
Okay. Yeah, thanks, man.
There is a question from Kishore Kumar.
No, that is
it's already answered.
Actually, so, I have a question, Dr. Arnab. Yeah.
Yes.
Yeah, Dr. Arnab, you showed very nicely about algorithms for mapping the snow mountains and on the Black Forest. These algorithms are totally different to map, snow on the mountains and to map the snow in the Black Forest.
So the core difference is, like I mentioned, Himalayas is very different from Black Forest. So Himalayas are at a high altitude. We don't have the problem of forest. So we can go ahead and use radar sensors over the Himalayas. But when we move to Black Forest and we try to use radar sensor, radar sensors are a bit funny because the information is not absolute. So signature from dry snow and the signature from forest can actually look pretty similar. But when you use optical sensors are very close to the true, spectral information. So that's why you go for optical sensors. And what we are doing is that we are combining, we are not letting the radar sensor go away. What we are doing is we are combining the radar information to understand the forest structure. So if you understand the forest structure from the radar information, because it's sensitive to the geometry of the canopy and other things, then you can determine what is the gap fraction in the forest, and that way you can tune your algorithm and know what to expect, how much of the signatures are getting affected, because whether the forest is dense or the forest is not so dense, these things will come from the radar, but the spectral information will come from the optical sensor.
Thank you, Dr. Arnab. I have another curious question, that is there any relation between this snow mapping and the global warming?
So I don't know how many, if we have like a climate expert in the audience, but I would like to say that when we talk about changes in the atmosphere and we say that this is a trend which is being influenced by us, which is being influenced by humans, we have to observe that for a long time period. You cannot say, of course we I mean, people will kill me if I say that nothing is we are not changing and just anything. But the thing is that you have to observe it for maybe thousands and maybe a million, because this is a time span for any geological change or any change related to. But what you can certainly do is you can observe what is happening right now. You can observe that yes, the ice shelves are calving out. Yes, the glaciers are disappearing. There is less and less snow over the mountains, and these things, of course. But if you ask me if we can relate directly to climate change, well, like I said, it's a question of a span of thousands of years, and unless we have made an observation in that scale.
Thank you.
Thank you.
Thank you very much. I think if there are no more questions, I request all of you to join me for appreciating his talk. Wonderful talk by Dr. Arnab Muhuri. Thank you so much. Yeah. So shall we break for about 5 minutes?
Yeah, of course.
Yeah. So we'll break for 5 minutes. I request all of you to come back, and then we'll begin with the third talk by Dr. Philip Wilke. Okay. Yeah. Dr. Philip Wilke to give his talk on fun with atoms, scanning tunnel microscopy of single atoms on surfaces. Dr. Philip Wilke.
Yeah. Thank you very much for the very nice introduction. It's a great pleasure to join this workshop. Let's talk about very small things. Let's talk about atoms. This is what I spend most of my day with. So I'm a physicist. I'm a nanoscientist, and if you would put me in a physics category, that is most of the time. Now wait a second. Somehow I have no okay, sorry. If you put me in a category of physics, then I would be a solid state physicist. This is somewhere between particle physics that you all probably know, which deals with the very, very tiny elements of matter, and astrophysics, which deals with large objects. And we are somewhere in the middle on the scale of atoms and collections of atoms. And what you see here is actually an image of a silicon surface, which is a very important material in semiconductor technology. And making these images of atoms is not, it's not hard, but it's also not trivial. And this is what I want to talk with you about, because we cannot simply use an optical microscope, zoom in and see an atom. And this does not work because of optical light. So the wavelength of light is actually, of visible light, is on the order of a couple of 100 nanometers. So it's much larger than actually atoms itself. And we could now go to other kinds of light, X-rays, for example, or we use a completely different technology to see atoms. And this is where scanning probe methods come in. And this works a little bit more like a blind person is seeing by reading Braille. But instead of using our fingers, we use a very, 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 very sharp metal tip that moves over a surface, almost touching it. And if we do that now and approach this tip, switch on a voltage, a bias voltage, then we can measure a current running from the sample to the tip. And if we now move this tip over the surface, we always get a little bit higher current when we are on top of an atom, as if we are not. So we get, if we now move across the surface, an electric current at the positions of atoms. And this is the so-called scanning tunneling microscope. For the experts, for the natural scientists among us, this is the quantum mechanical tunneling current. So the electrons are more hopping from the sample to the tip via an unallowed process, but this doesn't matter too much. So what we're getting is current maps. And if we're not doing this in one direction, but 2 dimensions, we can actually scan a crystal, its surface. For example, here, something that I've done during my PhD, the surface of a graphene sample. So graphene is a 2-dimensional form of carbon and forms a honeycomb lattice. So we can actually, in this matter, directly see atoms. See, of course, in quotation marks, because we're not using our eyes, but we can still feel them with the tip of our microscope. And this image here, this is only on the 3 nanometers. So for the non-natural scientists among us, let's put this in comparison, because this is very, very small. 1 nanometer is 1,000,000 times smaller than a millimeter. And to give you a perspective, you as a human being, you are between 1 and 2 meters, roughly. So your hair, that is actually between 10 and 100 micrometers. So this is 5 orders of magnitude smaller. But to reach the nanometer scale, we actually have to go another 5 orders of magnitude more down. So it's as if your hair had hair. That would be the nanometer scale. And this has been, so far, only been scientifically proven for Tom Selleck. The 2 physicists that have actually invented the scanning tunneling microscope are Georg Binnig and Heinrich Rohrer. They actually received the Nobel Prize in Physics in 1986 for this invention. And on the left side, you can see them with the first microscope that they were building. And on the right side, you see them shortly after the announcement of the Nobel Prize, just an hour or so later, with the IBM Zurich soccer team. And this is one of my favorite stories in science, of Nobel laureates. So I'd like to share that with you. What happened here? So they got announced for the Nobel Prize. They gave a press conference, but then they left because they had the game scheduled, the soccer game, because they were on the IBM Zurich soccer team against Dow Chemicals. So and this is just such a beautiful story. So the journalists followed them and took this picture. And it tells you a lot about priorities in life. So you should pay attention to your work-life balance. You should exercise, which is important. Never let down your teammates. And we Europeans, we just really, really love soccer. So those were the 2 guys who got the Nobel Prize in Physics for the scanning tunneling microscope. And actually, one of the first surfaces that they investigated was the surface of silicon, which is shown here in one of their very earliest publications in 1983. And the nice thing here is now that really the white spots in this image are the positions of single silicon atoms on the surface. So this technique now gives us a method to unravel the blueprint that Mother Nature has used to construct the fundamental building blocks of matter, that is atoms. And we can now see that. And we can not only image the surface of atoms, we can actually also now take our tip and scan across the surface. And if there's an object on top of it, we can keep our tunnel current constant or our electric current constant, and in this way see if atoms are on the top or even molecules or larger objects. And here's a small collection of my favorite images in nanoscience and technology. So here's an STM, a scanning tunneling microscopy image of actually copper PC, copper phthalocyanine molecules, and they have in the image actually very similar shape as in the chemical formula. Here's a nanotube image with a scanning tunneling microscope, or even more complex structures as quasi-crystals that you can also image, or even weirder, some molecules like to arrange in very particular shapes from the mathematicians in the audience. These are Sierpinski triangles that are forming from single molecules in just the way that they like to grow. So this is really not only useful to study how physics and chemistry are happening on a nanometer scale, but it is also very beautiful science that is happening here. But we can actually go one more step further. So we can not only image objects on the nanometer scale, we can also manipulate them. And the way this works is we can use our tip and pick up atoms and molecules from the surface and move them around on the surface. And one of the earliest examples for that is this here, where you see here an image with atoms on the surface, and subsequently researchers have assembled out of it the logo of the company or the lab that they're working for at the time, and this was the IBM lab. And what you're seeing here are single xenon atoms on a nickel surface. And I had the pleasure, so this was already 25 years ago, but I had the pleasure to work in this lab as part of my postdoc, not as my Feodolyn, but that was essentially, we moved the lab from IBM to South Korea. And the guy who was later running the lab, Andreas Heinrich, he was a successor and also was a Humboldt fellow for a long time at this lab at IBM. But we could not only image, or they did not only build the IBM logo, they also did the Star Trek logo, just because we can. And this is really not a big obstacle. They also made a very nice Valentine's card before I came, and even the world's smallest movie. So these are all single, in this case, CO molecules on the surface, and all these images are on the order of 5 nanometer or so. So this is really beautiful. It gives you a certain control of the fundamental building blocks of matter, that is atoms. However, we can actually also, we are trying to make something useful out of it. And this is, I want to tell you now, a little bit more research focused, what we have been doing in the last couple of years. Trying to use these capabilities for data storage. One example that I can give you is current data storage is already insanely advanced, what we have in our computers, but a typical transistor, the unit, one of the units in a computer that drives processing and data storage, is on the order of 10 nanometers at best right now. This is already insanely small, but it is still containing 100,000 atoms or so. And from our perspective, this is then, of course, still very large. Magnetic storage devices are even larger. And this is now the story of how we wanted to store information in the magnetic state of a holmium atom. For the non-natural scientists, for you, let's talk a little bit about what is a magnetic state, or what does that actually mean. So if you have a magnet and you break it apart, you actually don't get a red part, the north and the south pole. You get again 2 south and 2 north poles. And if you divide it again, this continues. But at some point, you have to ask, what is actually driving the magnetism here? And it turns out that physicists have found out that magnetism on the atomic scale is nothing but a spinning electron, an unpaired electron. So if you have a single electron, it will spin. That is the so-called spin of the electron. And this creates a magnetic field. There's also another kind of magnetic effect is if this electron is spinning around in proton. This is the so-called orbital magnetism. And these two can be combined. But for our purposes, these south and north poles are just up and down pointing electrons once you reach this fundamental up and down spinning clock, let's call it clock and counterclockwise spinning electrons on the atomic scale. And we actually did this for one particular atom on the surface. That was the so-called holmium atom. It's a rare earth element, which are usually the very strong magnets that we're seeing. And now we measured again our tunnel current across this, and we saw that it is actually switching. And we could then show that this switching corresponds actually to the magnetic state switching from the north side up to the south side up, meaning we changed the spin of this holmium atom. And what this was already on a very long time scale for our purposes. So usually on such a time scale or on such a length scale, everything starts to fluctuate a little bit. But these spins were already stable for tens of seconds. This is not a good storage device. So what we did is we made these measurements of how this switching between these two states is happening for different tunnel currents. And what we saw is that this time scale, the switching rate decreases when we decrease the tunnel current. So this time scale gets longer, the less tunnel current we're actually sending in here. And we found out that if we completely shut off this tunnel current, then this state would not switch anymore. And this is actually cool because we can, if we leave this spin alone, it will be completely stable. But if we increase the tunnel current just a little bit, it might switch into a different state. And if you think about what a bit is a 1 or a 0 that you, and it should be stable, but it should also be tunable. So you want to be switched, have it switched whenever you want it. So this is something that we had now. We could switch it whenever we switched, could increase the current, but we could also leave it completely alone. And to prove that, we actually we moved an iron atom next to our holmium atom. With these iron atoms, we can do something that is called electron spin resonance. The chemists and biologists probably know this word. It just means that we can measure the magnetic field from the holmium atom with the iron atom that is next to it. What we could do then is we could move our tip onto the holmium atom. We could run a current through it, in this way switch it to a different state. And then we saw that its magnetic properties changed by the resonance happening at a different position. And we could do this as long as we want. We could switch it back and forth. We even could, and this is changing because the magnetic field of the holmium next to it is changing. And we could even do this not for 1, but for 2 holmium atoms. And then this shift in the electron spin resonance is happening even more prominent, because now 2 atoms can be pointing in one direction or the other direction, or in a combination between it. And I would feel this change in the magnetic field at my iron sensor atom next to it. So this is the way how we could make very small storage devices that, and you see these holmium atoms, they are very close. They're just a couple of lattice sides of the substrate apart, so just about 1 nanometer. If you would scale this up to millions and millions of atoms, this would give you a storage density that could host the whole iTunes library on a device of the size of a credit card. Can we build such a device? No, we can't. So we can build 2 atoms. Otherwise, we would be rich. But we can show that it is possible. And this is not a trivial task, because on the scale of just 2 atoms, you got processes, physics that is in the way of them being stable. For example, quantum mechanics, where everything is very uncertain. And for bits, you don't want something that is uncertain. You want them to be stable, to store your information for eternity, ideally. So that is the story of 2 holmium atoms. And with that, the world's smallest magnetic storage device. This was done at IBM, and we then continued these types of experiments during my Humboldt Fellowship in South Korea. I am now at KIT, as mentioned in the beginning. If you want to learn more, this is my homepage, atomholics.de. And I hope I could show you how much fun I have with atoms, and hopefully you had some fun with atoms as well. But remember, you never should trust atoms, because they make up everything. Thank you very much.
Thank you very much, Dr. Philip, for a wonderful talk. And the talk is open for discussion now. Let me see.
Hi, Philip. I have a couple of questions, and I put it in the chat box. Can we do the measurements under in situ reaction conditions? That is, when we are dealing with, you said you can put single atoms and arrange them, So can we do say, for example, dissociation of, say, carbon dioxide molecule and see how it happens? Can we do that, under in situ conditions?
People are working towards, this is an field where on-surface chemistry is something that I'm not too much of an expert in, but people in the field are doing experiments in that direction. Now, the question is always, we have to so everything that I've shown that I didn't mention, this is under very controlled conditions. So this is at very low temperatures, close to absolute zero at 1 Kelvin. It's an ultra high vacuum, because otherwise you would have a lot of stuff on the surface. What you can do is you can have a molecule and you can make a voltage pulse, and then it might break apart. This is and then you might get energy scales for how much energy you need to dissociate a molecule from this very pristine conditions. So yes, that is certainly possible. Then the question is that really what a chemist want to have? Because usually a reaction is somewhat fuzzy and everything is moving. This is what this technique is not good, is because if something is moving and you scan with your tip, it might hop onto your tip. So that is usually what we don't like. So you want everything as stiff as possible. You can do this at room temperature, but it's much harder. That's just the name of the game. But yeah.
I understand. Yeah. My next question is: see, Moore's law predicts that the number of the storage capacity goes on increases every 2 years or so, actually.
Yeah.
So is it really still holds good, as with more and more nanomaterials are coming, and then the nanomaterial size also decreasing, and now it is more in the angstrom. I mean, what you are dealing is single atoms, molecule, they're all at angstrom level.
Yeah.
So the storage capacity, will it still increase with the size, with the decrease in size?
So this is the question where I'm actually, you shouldn't ask me, because this is all from the application side. So I told you that now as it would be a small storage device. But as I said, we are interested in, is it principally possible? But actually, in a wafer fabrication, you have completely different problems, and what they are doing is amazing. It's maybe, let's say in 40 years we are seeing something that we are now predicting here, that you could maybe store really something in a single atom or so. But then you would need to ask, it's always like you have to ask what is surrounding it, right? So you say we would need to have a gate or a device that is then still reading it out on a macroscopic scale. So this is much harder. So this is just essentially something to dream of.
Okay. No, why did I ask this question is, single atoms have a different behavior when it comes to catalysis, even for many other applications. So this is one of the hot topic in the area of catalysis, actually. That's why I asked, actually. Anyway, now there are another couple of questions. There is one Atul asked, actually, is the spin switching of holmium atom random on time scale is concerned, or becomes more regular with respect to tunneling current?
So the only switching that we are seeing so far is due to the tunnel current electrons. In the more physics term is, so we have the spin down state, we have the spin up state, and what you then typically have is an energy barrier that is between them. So what you're in fact doing is you're kicking out, you're having a tunnel current electron, and it kicks out this spin out of its ground state into another level, and from there it can either jump over the energy hill, the barrier, or tunnel somewhere through it through a higher state. We have not seen this process happening initially at our lowest temperature. So at some point, temperature becomes you can expect that the phonon, a lattice vibration, might kick it out of the state into the other state. A phonon, we did not see that really happening a lot, because the other problem is, so at 40-50 Kelvin, so 40 degrees Celsius above the absolute zero, these atoms also start moving on the surface. So this is the other problem why we are doing everything at low temperatures. We don't like movement. We like our atoms stiff on a fixed position, and they get kinetic energy when it's getting too hot.
Yeah.
Thank you. There is a next question by Dr. Abhay Kulkarni. Could you tell about life science applications for this technique? You must be a biologist.
Yes, that's a great question. So most honestly, the scanning tunneling microscope is not the perfect thing for life science. It's a little bit too unstable for that. But there is the cousin of the scanning tunneling microscope, which is the atomic force microscope. The force microscope measures a force instead of a tunnel current as a feedback, so it's really touching the surface somewhat. And this has to be this turned out to be more stable in atmosphere, in liquid, and there's a whole branch of that for life science. So, for example, one of the beautiful experiments is you can have DNA on the surface, and then you take your tip and you pull out on the DNA string. It's already worked. There's also 20 years long, but you can test the stiffness of a DNA molecule or image it. So this is more the technique to go for life science, just from the because it's more stable in the end.
Yeah. Thank you. There is a comment, not a question, from Rajiv Kumar. An excellent talk by Dr. Philip Wilke.
Thank you very much.
Yeah. So if there are no more questions, I think it's a wonderful talk by Dr. Philip Wilke, and he showed us the powerful scanning tunneling microscopy in various areas. Thank you very much, and please join me in appreciating his excellent talk.
Thank you for the invitation.
Thank you. Yeah.
My pleasure.
Yeah. So we'll go to the last fourth symposium by Dr. Paulina Seleka.
Yes, thank you very much. Yes, I'm there. I sadly can't share my video because it said that it's been stopped by the host. But hopefully sharing the screen will work. So.
Okay. Yeah, you can put on.
Yeah. I'm just trying now, so hopefully it will work.
I'm sure.
Okay.
Can you come?
No, she's trying. She's trying. Yeah.
She's trying. Okay.
You can see the option for share screen, and
yeah, Dr. Amrup, you can help her.
No, that's what I'm telling. So there is a button there, a share screen, and you can check that. And
she was there before.
Yeah, she is still there.
Still there, but not
she's
visible.
She is unable to share the screen.
Okay.
Maybe
sometimes it happens because of the Mac or laptop setting, maybe.
Oh, correct.
Can you please unmute yourself? We cannot hear you, Paul.
Can you hear me now?
Yeah. We can hear you.
Okay.
So now I'll try to share my screen with you. Hopefully this time it will work.
Yeah, it's coming now. Yeah.
Okay, that's good. So
now we can see the program file.
Yes. I'm trying to close it. Everything's here, everything under control.
There you go.
Okay, good. Yeah.
Now it should be, everything works?
Yes.
Very nice.
Okay.
Okay. Let me introduce Dr. Paulina. Yeah. Dr. Paulina Seleka obtained her PhD from University of Gdansk, Poland in 2016. Then she went to University of Cambridge, that's also called Wellcome's Sanger Institute in UK, to do her postdoctoral research. She focused her research on applications of single cell techniques to study hemopoietic cell differentiation and immune cell heterogeneity. Very recently, last year, she was awarded a Humboldt Fellowship and joined a Charité University of Medicine at Berlin. Currently, she is working on clonal hemopoiesis and influences of some cell state. I request Paulina to give her talk on attack of the clonal hematopoiesis at single resolution. Dr. Paulina.
Thank you very much. Hello, everyone. Thank you. At the beginning, I would like to thank you very much for the invitation. And I want to say that it's really my pleasure to talk about the project I'm currently carrying out at Charité, thanks to the support of Alexander von Humboldt Foundation. And my main interest includes studying blood cells, which are hematopoietic cells, using single-cell techniques. And single-cell techniques are exceptional as they provide the highest resolution by allowing you to identify changes which are affecting single cells in individual cells in the organism. And therefore, they have a great potential for biological discoveries. And I would like to start with explaining why actually it's important to study changes happening at the level of individual cells. If you look at the graph on the left, it shows the expression of certain gene across different cells. And what you can see is, for example, that cell 2 has a low expression of the gene, whereas cell 5 or cell 3 have the higher expression. And what is more important, if we take the average expression of, for example, 50 cells, this is not representative of any individual cells. So we can't really make the conclusions based on the expression looking at the population level. And we can also look at it from more everyday life perspective. And my favorite analogy when talking about single cell analysis is the one using smoothie and fruit salad. So basically, smoothie represents our bulk analysis. And what we see in the bulk analysis is that it's a mixture of the components. So in other words, by tasting the smoothie, we would be most probably able to say that there are some apples inside, but we wouldn't be able to say exactly how many apples or whether there were green apples or red apples. And if we really want to identify what kind of fruits we have, then we have to prepare a fruit salad. And fruit salad is our single cell level analysis, which when we perform it, we are able to identify the specific characteristic of the components. So for example, we are able to see that there are strawberries, bananas, and kiwi, and that the kiwi in the salad is the green kiwi, not the yellow kiwi. So single-cell omics technique are a relatively young group of methods, and they really took off in 2007 with the development of next-generation sequencing. And the first bona fide single-cell transcriptomic experiment, which looked at the RNA content and gene expression within a single cell, was in 2009. Then in 2012, the SMART-seq method was developed, which kind of automatized the single-cell transcriptomic and also improved the coverage, transcript coverage when looking within the transcripts. And in 2015, finally, 10x Genomics launched their first product, which allowed to investigate the transcript across 10,000 of cells. And right now, 10x Genomics is one of the leading companies in single-cell solutions. Over the last decade, single-cell methods underwent a developmental boom, which is clearly visible from this graph here. We can see that the number of papers using single-cell method, there's an increasing trend since 2010, with almost 5,000 papers published in 2019. The advances that has been made now allow to look at the different compartments of the single cell. It allows us to investigate changes in the DNA, in the transcriptome of the cells, which regards RNA. We can look at the epigenomics, which is modification of the DNA, for example, methylation, or of the protein content of a single cell. And measurements of multiple modalities within a single cell, like transcriptome, epigenome, genome, allows us to reconstruct the gene signaling networks and to better understand what actually is happening inside a single cell. And it can be useful, for example, in a cancer research, as cancer is a prototypical single cell disease where a cell starts to behave abnormally, and then it's triggered the whole cascades of problems, to put it boldly. Single cell methods are highly sensitive to molecularly characterize even a very small number of cells. Thus, they hold a promise for a clinical research field, as they can be used, for example, to improve patient stratification. And the impact of single-cell techniques is visible in a Human Cell Atlas initiative, showing that the scaling of single-cell technologies is ultimately applicable even to the entire human body. So, catalyzed by single-cell revolution, the Human Cell Atlas Global Consortium was launched in 2016 and is currently led by Sarah Teichmann from Wellcome Sanger Institute UK and Avi Fragiev from Broad Institute US. Human Cell Atlas is using high throughput technology at single cell resolution, and they're trying to map cells in the different human tissues, and it's some kind of like creating the Google Maps of entire human body. And this comprehensive research will be tremendously useful for the fields like biology and medicine, because the moment we have atlas of different cells within a human body in like a healthy individual, then everything can be compared to it, like a disease tissue. And that's gonna be a basic prerequisite to assess changes, for example, in aging, in a disease, or in the response to therapeutic treatment. And in the next slides, I will show you how we can use single-cell techniques to drive similar discoveries. So before actually moving into my current project, I will show you an example of single-cell approach driving discovery using zebrafish as a model. So zebrafish is a small fish. It's a perfect model organism for hematological studies because it is small, the embryos are transparent, so it's easy with the visualization. And even though it looks completely not like human, lots of genes which are actually involved in the development of the blood are similar within human and zebrafish. And this data, which I'm showing you here, is from my very first project I performed at University of Cambridge when I started my single-cell adventure. And I know that it's kind of complicated slide, but please bear with me. We were, so in that particular project, we were asking the question whether a specific populations of immune cells that were identified in mammals are also present in zebrafish. And that was important from an evolutionary point of view, because it would say whether the presence of this population is already identified in lower vertebrates, or whether it's a specific adaptation of mammalian immune system. And to achieve that, so to look for the certain population, we performed a single-cell RNA sequencing on immune cells isolated from the gut of zebrafish. And from the previous studies in mammals, we knew that there are three main types of cells we are looking for, and those types of cells produce different cytokines, different substances upon the immunological stimuli. Therefore, we developed a short-term inflammation model, and we injected our fish here either with PBS, which is like harmless buffer, or bacteria extract, or worm extract. And the analysis revealed the presence of population of different cells. And this is visible here in the upper panel. So each dot on the graph represents one single cell, and the cells from the same cell type are colored from the same clusters, which are having the same color here. And the lower panel here shows the expression of the genes across different clusters, which means across different cell types. And based on the expression pattern, we were able to identify the cluster of cells, which kind of resembles the mammalian population we were looking for. So in the next step, we ask whether the cells we saw in those three conditions are really different cell type, because as I already mentioned, in mammals, there are three main major cell types, or whether it is the same cell type, which simply differs in the expression profile due to the immunological stimulation. And to answer that, we perform alignment of the data, and this slide here explains briefly how the alignment strategy works. So in all three conditions, so in our case, it was PBS injected fish, this harmless buffer, worms injected fish, or bacteria injected fish, the same cell types are present. And cell types are represented here by the same shape. What changes after we inject the fish with the stimuli, it's a cell state, which is reflected here with different colors. And what alignment strategy actually does is clusters the cells together, the same cell types. So what you can see here is that the cells with the same shape cluster together regardless of their different colors. Therefore, this alignment strategy allows us to look at the changes in the transcriptome related to stimulation. And if we go back to our original data set with the zebrafish, we applied this alignment strategy, and we saw that the population of cells from 3 different conditions actually clustered together. And the difference in the expression of different genes we observed, the different cytokines, was actually stemming from the immunological challenge. And this proves that the cytokine production reflects changes in cell state triggered by the different stimulus. And as a consequence, it suggests that instead of having 3 different established populations, like it happens in mammalian immune system, in zebrafish, zebrafish actually has 1 population of the cells and produce the different cytokines like on demand, depending on the environment. So this suggests that the population we discovered in zebrafish might serve as evolutionary precursor of mammalian cells, which further developed into 3 different populations during the evolution. And these examples actually illustrates the power of single cell techniques to discover new population of cells, and especially difference in the behavior related to the specific condition, which can also be applied to the clinical field. So for example, when we investigate the response of a specific cell population to a treatment. And now when you are more or less familiar with single cell techniques and what kind of actual discoveries are possible using them, let's go back to my current project and finally talk about attack of the clones from the title stock. So in body, all the mature blood cell types are coming from a hematopoietic stem cells. And different mature blood cells in the body have different functions. So for example, white blood cells like macrophages or lymphocytes, they protect our body from inviting pathogens like bacteria or recently hotter topic viruses. Whereas red blood cells, erythrocytes, they are responsible for transporting the oxygen. And typically, hematopoietic stem cell and progenitor cells are equally capable of producing all of the different blood cell types. And therefore, they are maintaining the healthy state of polyclonal hematopoiesis. And that can change the moment the hematopoietic stem cell acquires a somatic mutation, and somatic mutation is represented here with the red star. So what is important to bear in mind here is all the mature blood cells which are coming from the cell with the mutation will also actually have the same mutation. And additionally, the presence of this mutation can give a stem cell a fitness advantage, which means that it's going to proliferate more, producing more progenitor cells. And that will lead to the fact that the big proportion of the mature blood cells will actually have the mutation. And that phenomenon is called clonal hematopoiesis, and it's an age-related condition where above 10% of the people over 60 have clonal hematopoiesis. So as I already mentioned, clonal hematopoiesis is characterized by the presence of somatic mutation in the blood of otherwise healthy individuals. We don't consider clonal hematopoiesis as a disease. So if it's not considered to be disease, why we are interested in it? Well, the problem now is that the modern society is getting older, and between 10 to 30% of all elderly people do have clonal hematopoiesis, and clonal hematopoiesis is associated with the increased risk of blood cancer and cardiovascular disease, which overall leads to increased mortality, or to put it boldly, if you have clonal hematopoiesis, your chances of dying prematurely are higher. Therefore, understanding the causes of clonal hematopoiesis and how somatic mutations influence the transcriptome in relation to cell identity, cell type, can actually provide critical insight into mechanisms underlying the increased overall mortality of people affected with clonal hematopoiesis. And this is actually what my project at Charité is about. So in terms of clonal hematopoiesis, it is totally unknown what impact different somatic mutations have on different cells. So for example, it can have a different impact on lymphocytes, or a different impact on macrophages. So to fully understand how the presence of somatic mutation influences cells function, I will apply single-cell transcriptomic to dissect how clonal hematopoiesis affected changes influence the transcriptome or different mature blood cell types. And it will help to answer the question whether the presence of the mutations has a direct impact on the genes engaged in inflammation process, as disturbed inflammation is actually emerges as a culprit behind increased risk of heart disease. And apart from investigating only transcriptome, I will also check the epigenetic changes, in that case, the changes in methylome, as during hematopoiesis, the methylation pattern is directly linked to the plasticity of developed blood cells, which means that also changes in methylation can affect the expression of certain genes in the mature blood cell types. And detected clonal hematopoiesis at various molecular levels, and in that case, that would be epigenetic and transcriptomics. This is providing more data to understand the influence of the mutation, as each of these omic data can actually reveal useful marker of the process and give an insight into the perturbed biological pathways. Finally, to directly investigate the impact of clonal hematopoiesis on the cell function, I will also culture the hematopoietic cells in vitro and then look at the mature blood cells derived from them, as recent study has shown that hematopoietic cells can exhibit lineage biases. So they can produce more myeloid cells comparing to the lymphoid cells, or in more balanced hematopoiesis. And what is interesting, that actually myeloid biased hematopoiesis, which means production of more myeloid cells at the expense of lymphoid cells, is also age-related condition, the same as a clonal hematopoiesis. So this is to validate whether the presence of the mutation is actually triggering the myeloid biased hematopoiesis. So now the question is how exactly I will do that. So to dissect the influence mutation of the transcriptome, I will apply 10x technology, which this is a kind of a technology which allows to investigate thousands of cells. And this technology allows to capture single cells in a special droplets. And within each droplet, there's a cell, and there is also special barcoded bits, which serves as a tag specific to a cell. And this procedure is slightly modified. I won't go into the details, just so we can also get the information about the specific mutations. And after the libraries are prepared, they undergo the sequencing, and we can analyze the data in a similar way as I showed you for zebrafish example. And this analysis will allow us to identify different cell types, like here demonstrated, and it will also be able to show us which cells within the cluster do have the mutation, because we don't expect that every single cell will actually have the mutation, and identification of the cells with the mutation across cells different cell type is important, as it will allow us to directly investigate the changes the mutation causes in cell-specific manner. So for example, we can take a cluster of macrophages and then run differentially expressed gene analysis. And for example, we can see whether the presence of the mutation is linked with the upregulation of pro-inflammatory genes. Moving forward to the methylation analysis, the experimental setup will allow us to generate information about the transcriptome profile, mutation status, and also the methylation from the same cell. And analysis of the methylation profile data will provide additional information about changes in methylation profile of CpG island between mutant cells and the wild type cell, like similar I showed you in the previous slide. And CpG islands are parts of the genome which are characterized by the repeat of CpG denucleotides, and they're likely the most informative elements of DNA and methylation. And the insight into those differentially methylated region level around protein coding gene will provide additional information about possible epigenetic mechanisms that are underlying clonal expansion of the blood progenitors and inflammatory properties of the blood cells. And last but not least, I will also investigate the influence of the mutation on lineage bias. So as I already mentioned, all mature blood cell types, you saw this picture before, are generated from the hematopoietic stem cells. And to see whether the presence of the mutation affect basically what kind of cells are coming from this hematopoietic stem cell, we are sort single cell into the wells, and then we will culture them in the condition which allows them to develop all different cell types. And after that, we'll harvest the colonies which are coming from one single cell, and we will be able to, using flow cytometry method, to identify what kind of cells we are getting. And in that case, after we will sequence the DNA of the cells deriving from each colony, we will know which cells were bearing the mutation, which are not, and whether the presence of the mutation affected the cells which were generated. So basically, summarizing in this project, we will apply single cell technologies to study clonal hematopoiesis, its influence on the transcriptome, methylome, and lineage bias. And basically, it will give us information of the influence of the somatic mutation on blood cells' behavior and their functions. And we do anticipate that results will provide important answer to the question of how somatic mutation influence the transcriptome of different blood lineages and reveal the mechanism underlying the clonal expansion. And at the end, I would like to thank all the people without whom this research would not be possible. So the big thanks to the Cambridge team, where I started my adventure with single cell techniques, and to Charité team, where I'm actually currently continuing this adventure thanks to the support of Alexander von Humboldt Foundation. Thank you very much for your attention.
Thank you very much, Dr. Paulina. There are, for the excellent talk, there are a couple of questions. One is from...
we can ask Srivatsan to take care.
Yeah.
Srivatsan?
So one is from...
Yes.
Can I take care? Okay, I can, yeah.
No, it's okay, yeah. I can do that. So one is from Rajiv Kumar. Can non-invasive SCA detect different receptors present on cell?
Well,
so can we differentiate normal resting cell and tumor cells?
So the problem is with this one, it's depending, because the presence of the somatic mutation does not actually changes the expression of the mutation on the cell, like on the cell receptors. Because if it could, our life would be easier, as we wouldn't have to look inside of the cells to change. We would be able to develop the antibody against the different receptors on the surface of the cell, and then sort out the specific population. So because those mutations I was talking about, they are not affecting the surface protein, then we cannot really do that, if that's answered your question.
Thank you. The next one is from Jyoti Otageri. Why would one use a zebra fish for single cell omics? If the closer
so this is actually excellent question. I really love this question. So that's the problem, because when you look at zebrafish and human, they're totally different. They're absolutely not similar. But all the biology behind developing the blood cells, it's like the genes within the zebrafish and the human are really conserved. So zebrafish actually, especially when answering very basic biological questions, zebrafish are excellent model for that, especially that, for example, embryos are transparent. So if you have a transgenic zebrafish line, you can actually, and mark the population of cells, you can visualize them in the embryo.
Yeah. So the continuation with the same question, if the closer human relative mouse or rat model may give information more useful for application for humans.
So that's actually a problem, because in some cases you can study stuff in mouse and in rats. But for example, in Fanconi anemia, if you try to model this disease in mouse, the embryos are not viable, so you can't really. And with zebrafish, and we actually have a model of Fanconi anemia of zebrafish, the embryos are viable and the phenotype of the disease is actually similar to the human phenotype of the disease. So that's really depends on your biological question, but zebrafish are a really great model for hematology.
Thank you. The next one is from Atul. Do you think the epigenetic changes, for example, gene methylation pattern in HSCs would be propagated downstream into the differentiated cells?
Yes, it can be. And actually there was like lots of paper recently showing that actually epigenetic marks are great, are even better at predicting like the aging process, and they are great markers of aging process. That's why we are also interested. And in terms of clonal hematopoiesis, two most affected genes which actually have the mutation are the epigenetic regulators, regulators of actually methylation. So that's why it's basically investigating at the epigenetic level can also bring like the new layer of understanding.
Oh, he also compliments for the interesting talk for you.
Thank you very much.
The next question is from Abhay Kulkarni. If clonal hematopoiesis is epigenetic in origin, can anti-aging molecules change this fate?
Well, this is what we are trying to actually, when we have the results of that, then we'll be like, I will be much better. Maybe in 1 year, I will be better at answering the question, because then we'll actually see what actually happens.
Yeah, thank you. The next question is from Atul. Do you think the epigenetic changes or gene methylation pattern? Okay, so I'm sorry, the next one. Jyoti Otagiri, also, what are the disadvantages of single cell omics?
Yes, so the main disadvantage is, especially at the beginning, and all the reviewers are always pointing that out, that it's a descriptive analysis. So you can't really, the moment you are getting the cell, so I can't have I was showing you that we're going to be investigating transcriptome and epigenome, and also like separately the lineage output. Because the disadvantage is that when I'm taking single cell for the analysis of the transcriptome and epigenome, I'm lysing the cell. So the cell is no more viable. So I can't, on this particular special cell, perform the functional studies. And also analysis of the single cell data, it's really challenging, because you are basically getting the material from one cell. So there are lots of dropouts. So it's like now their methods, computational methods for analyzing are getting much better. But the problem is that sometimes you have a dropout of the gene and you don't see the expression, and then you don't know whether it's actually biologically informative. The cell is not expressing, and there's just the limitation of the detection.
Thank you. The last one is from Kishore Kumar. I heard in some cases, gene duplication is it serious?
So that's really depends. So in clonal hematopoiesis, it's a somatic mutation, not gene duplication. But especially in some cancers, you have copy number variation, and then there might be a gene duplication. And they're also right now developing the single cell techniques to look at the actual copy number variation. But this one is more difficult, is that, for example, single cell transcriptomics, because in one single cell, you have one copy of the DNA. If genes can be expressed like has higher expression level, lower expression level. But when you just when you look at the RNA, but when you look at the DNA, it is one copy, and that's why like the detection limit is a problem. But those methods like are getting better and better.
Thank you. The last one is again a compliment for you from JT.
Thank you.
Buddy, can I ask a question?
Oh, fine. Yeah, you can.
Yeah, it's a nice talk, and I know this field is quite new, and then it's quite contemporary, right? So. Yeah. The thing is that how do you barcode the cells so that you can sort it out? It's a more technical.
So basically what you do for the STENX technology, for example, so you have to amplify your RNA, and each mRNA has a poly-A tail. So there are the primers, which are like poly-DT, and they are attaching to this poly-A, and from one side of the primer you can also attach the barcode. And in different, for example, in 10x, they will have like, because of the amplification and synthesis of the RNA, and like in PCR reaction, those cells will retain this barcode.
Okay, and these barcodes are fluorescent, right?
No, they're not. They're actually special tags. Like when you then do the sequencing, you can analyze. There's like a special sequence.
No, but then how? See, these are inside the cell. But then how do you actually sort the individual cells? Because you have to sort the individual cells, and then you do the sequencing.
Yes. So this is like basically what you do. This 10x machine. It's a fluidic setup, it's actually like you are putting the plate inside the cell, and it's able to, you're putting your cell solution with other reagents, and this fluidic system is able to put one cell and one barcode into one droplet.
Okay.
And so you're not sorting like individual, like a 10x.
So, and this barcode is actually transfected in that single cell.
Yes.
Okay, so that's fine. That's fine. So because we also have an instrument, so one of our colleagues is working on it, and then we are actually trying to develop click chemistry to actually tag these poly-A tails and other things. And also we do some imaging and other things, but then we are also using click chemistry to actually label endogenous RNAs and other things. And we are thinking if we can use this kind of a flow kind of a system to actually look or develop technologies actually for sorting out or picking up these individual sequences. Nice. Okay. Thanks, buddy.
Thank you.
Thank you. There's the last question by Atul. How to explain epigenetic heterogeneity for a given gene if present among single cell HSC population?
So that's really depends, because like the cells are not individual entity, and they are like for blood cells, they're for example in blood in the bone marrow. So also like the cells with this one singular blood can interact with can kind of also influence, especially this is especially visible like in epigenetic changes. So basically the environment of the cell can influence the epigenetic changes.
Thank you, Dr. Paulina. I think it was an excellent talk.
Thank you.
Please join me for appreciating her talk with the usual style, So with this, we conclude all the 4 seminars, and all the support talks were excellent, right from frugal innovation by Louis Fisher, and Dr. Arnab talked about the snow capping in mountains in Black Forest, and of course, then Dr. Philip talked about scanner-tunnel microscopy, how powerful it is, and fun with atoms, and the last one, Paulina talked about the hematopoiesis, clonal hematopoiesis. So thank you so much for all I would like to thank all the speakers. So with this, we conclude this session. I would give it to Dr. Srivatsan for the vote of thanks.
Hey, thanks, buddy, for organizing or taking care of this session. And Gopi, you wanted to say something before I give the vote of thanks?
Yeah, please go ahead. Yeah.
So you don't have to say, you have said all. Okay, so it's a great pleasure to be part of this mini symposium, and also it's a pleasure to give the vote of thanks. And as Gopi and Professor B.S.M. Rao had already told, that the mandate of this symposium is to actually bring researchers, policymakers, institution builders as before. And now I've got a new word, actually, human geographer. I never knew about it, but then I know geography and geographer, but then human geographer. And we could bring all of you on one platform and actually listen to your research and your experience about what is research is about. And of course, it's a very general conference, and and it's good to know about others' research, not just your own, which usually happens in a focused conference. And I usually get to know about a lot of different things through these conferences and what others are doing. And before concluding, I would like to thank Professor B.S.M. Rao, the president of Humboldt Academy, Badigar and Gopinath for actually initiating this whole process. And also I would like to thank Ramru for taking care of all this Zoom meeting and organizing these online virtual symposium. And with that, I would conclude and as well as thank all of you. And especially any conference, for a successful conference, you need good speakers. And I thank all the speakers from Germany for taking their valuable time and then getting in touch with us and giving this wonderful their wonderful talks. Thank you all. And then with that, we conclude this mini symposium, and I wish a very good evening, and then stay safe, and then with mask for the Indian guys. And I know Germans, you are already hiking and going to schools and colleges, but we have not started yet. Yeah, we usually after this kind of a mini symposium, we usually, have a dinner with a lot of other activities. Okay, good ones. But then, this time it's not so possible. Be next time.
Thank you very much. Yeah.
Thank you. Thank you very much. Anything else, Gopi, you want to say? Otherwise, we will close the session.
Yeah, we'll close the session. Yeah. Thank you very much to all the speakers again.
Okay.
Thank you very much.
Thank you.
Yeah.
It was a pleasure.
Thank you all.
See you next time.
Thanks, Philip.
Yeah.
Thanks, Anurag. Thanks.
Thank you. It was
Paulina.
nice meeting you all.
Thank you all.
Thanks.
Bye-bye.